It's around 5. So, welcome everyone. So, myself Durga Prasad. So, I'll be taking the live sessions for the course on fundamentals of convective heat transfer. A bit about myself. I am a PMRF scholar from Department of Mechanical Engineering, IIT Madras, and currently I'm in my final year of my PhD, and I'm working on application of computational fluid dynamics to understand the thermal and fluid dynamics of flows inside buildings and glazing systems. And for this particular session, this will be happening every Saturday for the upcoming 12 weeks from 5 to 7 p.m. And the meeting link will order be circulated to all the registered students. All the live sessions will be recorded. And if you miss the session during the live, then you can access the recordings on the YouTube link. And this session, along with the slides, whatever I'm discussing here, will also be uploaded on a Google Drive link that will be shared with you. If you have any doubts or queries regarding the live sessions or you have any feedback, you can always write to me at me22t400@smail.itm.ac.in. If you have questions, anything other than related to live sessions, say something regarding assignments or exams, or if you find any queries with respect to the recorded sessions, you can raise the question on the discussion forum, which is available on the course website. So on the course website, you can find the problem solving session recording here. If you click on this, it will redirect you to a Google Sheet link where you will find the YouTube link of the recorded session, as well as the Google Drive link where you will find the uploaded PDFs of whatever we are discussing in the live sessions. And the discussion forum can be accessed from the Q&A here. Maybe we'll wait for a couple of, this is a general introduction. So the first week of the particular course is mainly essentially to motivate you towards the necessity of this course, to familiarize you with what to expect from the course and what to expect from this particular live sessions. So the general introduction about the course, in this particular course, we'll be discussing forced natural convection flows in internal and external. We will discuss what these terms individually mean. And then we'll also, essentially the course is more analytical in nature, where the governing equations for each of these cases under certain assumptions will be derived in the recorded sessions that you will be accessing as discussed by the professor. And then he will also discuss some of the example problems to understand, to connect whatever we have derived to solve them. And some techniques will also be discussed, numerical as well as analytical techniques to solve the differential equations that we will be deriving in the as the course progresses. And the aim of these live sessions is to help you understand if you have any queries in the recorded sessions, or if you need some elaborate discussion on any particular concept, you can bring them up in the live session. And also, if you have any questions in the assignments that are already completed, like since assignments are graded, we won't be discussing the assignment questions as is. But if you have any queries regarding what the question means or anything in that particular manner, we can discuss those things also in the live sessions. If you do not have any queries, the general progression will be like I'll be discussing on give a general summary of what is discussed in the lecture videos, and then I'll take up some of the previous year problems or some example problems from some reference textbooks so that you can understand better the concepts that are discussed in the lecture videos. And again, just to be more emphasizing, this course is not like there is a CFT section also in this particular course, but it is not a full-fledged CFT course as such. You have to take separate courses for that. So the main idea for this course is to bring you to the basics of convective heat transfer. So it is like learning alphabets of convective heat transfer, and then how to connect them to make little words out of it. The real application will come as you take more and more courses in this particular one. The intended audience are the postgraduate in UG from mechanical or any other similar branches that deal with convective heat transfer. And the main idea is for faculty members or practicing engineers who wants to brush up their concepts on convective heat transfer can also take this course. And as I said, this course is more analytical in nature, so we will be deriving most of the governing equations, and the assumptions that are involved in deriving those equations are what will be more stressed inside this particular course. Prerequisites require you to understand the basic knowledge of mathematics. Essentially, I mean the differential equations. You need vector calculus, also a little bit of vector calculus, essentially to understand the notation that we'll be using in the course, and a little bit of integration. Linear algebra is also kind of, as long as you know how to solve a set of linear equation. basic techniques also work. This should be sufficient for this particular course. And even if you are not aware of these techniques, please brush up on those topics. We will also have brief, whenever these things come into picture, we will have a brief discussion on them. If you have any queries, we can discuss them then and there. And then we also need to understand heat conduction, which will not be covered in depth in this particular course. As long as you know Fourier's law of conduction, that should be fine, because that comes in the derivation of energy equation, which comes in the upcoming week. And basic knowledge of fluid mechanics, which essentially involves derivation of continuity, momentum equations, which will not be covered in this particular course. It is assumed that you can brush up on those concepts again, how the Navier-Stokes equation comes and what are the assumptions under which that we can reduce it. Like, we will be using some assumptions, so you should familiarize yourself with those assumptions. If you have any queries, please to raise them when the particular session is coming up. The reference textbooks are the same as provided on the course website. I'll be closely following based on textbook. The example problems from this I'll be discussing. But if you do have any other queries, you can follow any other book. And if you have any questions or something, you can raise them or you can write to me before, so I can come prepared for with those questions and we can discuss them during the session. Okay, before going on to the general summary of what is discussed in this session, do you have any specific questions that you want to ask, or do you have any expectations from this particular course? And also, I would like to know the background of all the students. So maybe you can type in the chat box, that is also fine. Or you can unmute yourself, whichever is convenient to you. You can just type the department you are from and what you are expecting from this particular course. If it aligns with whatever I have mentioned before, it's fine. And we can also take up some additional things that are not covered in the recorded sessions, as in like some of the numerical techniques to solve the equations are not discussed in detail, and we can take them up also in the live sessions when the time permits. You can just type them in the chat box. I'll wait for a couple of minutes. Okay, sure. As a coursework, okay. Okay, so you're from maths department. Fine. Okay. Anyone else? Thanks for responding. So this is a coursework for you. So I hope you have done some heat transfer course in your math department, or is the first kind of a heat transfer course as such? Like, you're familiar with fluid mechanics? Okay. So you have the prerequisites. So your main topic is fluid dynamics. Okay. And about heat transfer? Okay, since you are already from fluid mechanics, so then it should be straightforward. So the only additional things from the heat transfer. So in this particular week, the lecture video discusses like the basic applications of convective heat transfer and the motivation for this particular course. So just to quickly summarize what has been discussed in the lecture videos, it starts with something about different modes of heat transfer. So heat transfer is essentially energy transfer happening due to temperature difference. T is my temperature field and delta T is my temperature difference. So if energy transfer is happening owing to the temperature difference, then we call it heat transfer. So there are three different modes of heat transfer. And hope, have you already gone through the lecture videos before joining the session? Okay. So this will serve more like a recap of what you've already gone through. So we essentially have three different kinds of modes of heat transfer, depending on how the energy is transferred between two surfaces with the different temperatures. So it is a conduction, convection, or radiation. In conduction, we have essentially this is a diffusion process. Convection is essentially conduction plus an advection. So we'll have a bulk fluid motion that will transport the heat energy. And radiation is without any mediums, it is through electromagnetic radiation. For this particular course, we will skip the radiation, so we'll be only dealing with conduction and convection. So what is the difference between diffusion versus advection? Let's say if we want to speak mathematically, how would if the heat transfer is denoted by Q double prime, which is heat transfer per unit area, unit watt per square meter. A diffusion process is one where the vector or the whatever is the driving field is related with respect to the gradient of the driving field. So if T is my temperature field, grad T is my temperature gradient. So the heat flux will be proportional to grad T. So the Fourier law of conduction gives us Q double prime is minus kappa times grad T, where this is my thermal conductivity. Conduction is purely a diffusion process, so there wouldn't be any direction as such. So what I mean by there is no direction as such is it is happening only because of temperature gradient, not it doesn't depend on the actual temperature values. The thermal conductivity itself could be a function of temperature, but not the net heat flux. And then comes convection, which is a component which is consists of both conduction as well as advection. So convection requires a heat source. Let's say I have a wall, and then there is some fluid surrounding the wall. If the wall temperature is Tw and the fluid surrounding it is at a temperature T infinity, such that the wall is at a higher temperature than the ambient temperature, then what would happen is heat would transfer from the solid into the fluid. And the fluid particles will take the energy from here and then they will move in depending on certain conditions, there will be some flow happening here. So what we will be interested in convection is what is the net amount of heat that is transferred from the wall into the fluid. So whenever we have a solid in contact with a fluid, we need to solve this problem as like we can solve this problem as a conjugate heat transfer where at the interface we need to maintain two conditions as the continuity of temperature as well as the continuity of the heat flux. So at the interface we have whatever is the temperature of the solid should be equal to the temperature of the fluid, and we also need to maintain the heat flux being the same. So whatever is the heat that is transferred from the solid should be the amount of heat that is gained by the fluid. So that would be similarly that should be equal to where the K and gradient of T everything should be measured inside the fluid on the RHS, and for LHS the K and grade T are all calculated from within the solid properties itself. Again, it is important to note here that this particular equation is written at the interface. At the interface, we are writing it as only conduction. So within the fluid, at the interface, it will be purely conduction. But as we go further away from the wall, then we will have other things also coming into picture, which is what we will be discussing in the next week. In general, what we do is we use Newton law of cooling, which simplifies this entire thing, and we will say that the net heat flux will be given by H times Tw minus T infinite, where H is called the heat transfer coefficient. Unlike the thermal conductivity, heat transfer coefficient is not a constant, but it is going to be a function of several things, including the properties of the fluid. This is going to depend on fluid properties. It also depends on flow properties. It would also depend on geometry, or basically I can call it the configuration of the particular problem. So in most of the convective heat transfer, like whatever we'll be discussing in upcoming weeks, is about finding out either this Q double prime, which is the heat flux, or finding out the temperature. So essentially, it will boil down to eventually knowing the heat transfer coefficient. So this is only one equation we have. So at most we can have one unknown. So the remaining two things have to be specified to us. So usually this heat transfer coefficient will be computed in terms of temperature difference. So entirely we'll be having one equation. So either if temperature is given, you will be asked to find the heat flux, or the other way around. But this H, because it is a function of fluid and flow and geometry, like different things, we will be having different values of the heat transfer coefficient and different techniques to evaluate this H depending on the particular configuration that we are interested in. So what is the difference between fluid properties and flow properties? Any example for fluid properties? Say in this particular case that I have to, or we can take an application. Say for example, now if you are sitting in a room, consider this as your room and this is your desk. We have an air conditioning system from which air comes in and air goes out, and some flow happens inside this. So out of for this particular configuration that we are seeing, and I'm not sure if you have a familiar concept in math. So whenever we discuss problems of this, we have the concept of a control volume or a system. Essentially, we divide the entire problem into two things: one, our region of interest, and everything else. So in this particular case, my region of interest is whatever is inside my dotted lines, and whatever crosses that region of like everything else is my surroundings. So within my region of interest, so everything here is what we are trying to model from whatever equations we are writing, and everywhere at the boundaries is what will be uh, given. Like this is essentially like this will be my governing equations and this will be my boundary conditions. So in this particular case, the net heat transfer, let's say from the wall or from this particular surface, whatever we are, say if I kind of draw my boundary like this, there will be net heat transfer from whoever is sitting inside the room. So that is given by the net heat transfer coefficient times Tw minus T infinity, where Tw is the temperature of that hot object and T infinity is the temperature of the ambient. Now this H is going to depend on these three configurations, like configuration, flow and fluid properties. So fluid properties like density, rho, viscosity. These are the fluid properties. So what are the flow properties? Is the question clear? Say for example, the type of flow, laminar versus turbulent, depending on if it is a laminar, you would have one heat transfer coefficient. If it's turbulent, you would have a different heat transfer coefficient for the same geometry and for the same fluid properties. So what decides that again is something that we'll be discussing in this particular course. How do you differentiate this laminar versus turbulent flow, and what are the quantifiable things that we can measure, some kind of non-dimensional numbers that we can use to identify the transition from laminar to turbulent, and so on. And there are different kinds of other kinds of flows also, which we'll also discuss in the upcoming slides. So the basic idea here is essentially we have three modes of heat transfer, of which in this particular course we will only discuss conduction, convection, and that too convection is the dominant one. Conduction will only be used like a couple of times just to kind of derive the energy equation, and wherever we have interfaces, just near the interface, we will have the conduction being the dominant mode of heat transfer than the convection. So that is the only thing where conduction is required. And the next is the general applications of convective heat transfer. So where is convective heat transfer being seen in nature as well as in industrial applications? We have several applications. So one of them is, let's say, the room example that I've just told you. So if you're sitting in a room, so you will be releasing certain amount of heat that will be carried away by the air that is circulating in the room. So the question now that we need to answer is, every person, like depending on your metabolic rate and whatever your activity state is, you are going to release a certain amount of heat. The question now is how much of that heat can actually be taken by the air that is being circulated inside the room. So if you emit around 100 watts of heat and the air capacity is only 50 watts of heat that it can take because of whatever configuration you have, then that would essentially result in net increase in the temperature of the room. So how do we estimate the amount of heat that the air can take depending on this configuration? And so here this problem would essentially boil down to determining Q double prime given a particular temperature, or it would be other way around. Determine the, like, we know what is a comfortable temperature, so what is the maximum Q that you can take, or you have a certain amount of load, so in order to get a certain amount of temperature, what should be my heat transfer coefficient, which, as I said again, is going to be a function of fluid and flow property. So we will decide what flow properties, or what should be the velocity that I should be sending the fluid here in. That would be one flow property. Depending on that, it will decide if the heat can be extracted from the room or not. So in order to understand that also, we would be requiring, and we need to have an understanding of what the heat transfer coefficient is and how convective heat transfer is important in this particular application. There are other industrial applications also. One of the common one is the heat exchangers, where you have two fluids, a hot fluid which and a cold fluid, let's say a concentric one. So if if this is one of the fluid, and then we have another fluid flowing in the tube concentric to the outer one. So then what will be the net heat transfer between these? What would be the temperature of this plate? These are all the questions that we need to answer. So if I need a certain amount of a heat load, what should be my inlet temperature? Or if I have certain material constraints that tell me that this material cannot go beyond a particular temperature, then how much is the maximum heat load I can go to? What should be the length of the heat exchanger? These are all different questions that we need answers for. And in order to quantify them more appropriately, we would be requiring this particular course. There are even more applications that are discussed in the lecture videos. You can go through them. If you have any specific questions or anything that is related to to those who are seeing the recorded lecture, the recorded session on YouTube, you can also go through the sessions. And if you have anything particular that is in your research interest, you can also point them out. And if we can also discuss them in detail, like what are the problems that you have, you can also bring them up and we can have discussion on that. And then we have different flow classifications. As I said, the first type of classification is depending on who is originating the flow. So we have certain flow. It can be who is the main driver of the flow. It can be because of that, like you put some fan, pump, or something. Essentially, because you're putting a pressure difference across the boundaries. So if I have a certain boundary like this, and then there is a fluid inside, And if across the boundaries I have a pressure difference that is kind of driving the fluid motion inside this domain, then I would call this a forced convection problem. Or instead of the driving forces being at the boundaries, if they are body forces, like say gravity or basically buoyancy force, where you will have a density difference within this that is actually causing the fluid motion, then that would be called natural convection. In general, both of them happen simultaneously, so you call them mixed. So even under normal situations, we have both of them together, but the relative strength of these is not always uniform. So depending on the relative strength of this, we can either use the forced or like it will shift either towards a forced or natural convection. To ascertain the relative strength of this, we use the concept of non-dimensional numbers, which you might already be familiar with in fluid mechanics. We have different non-dimensional numbers. For this particular one, we will use let's say for Richardson number, which is where GR is the Grashof number and this is the Reynolds number. Grashof number is again given by the ratio of buoyancy to viscous forces, where buoyancy forces will be the gravity times thermal expansion coefficient times temperature difference. And then we'll have some length scale and towards to the viscous forces. And Reynolds number is again inertial to viscous forces. Inertial is U infinity times U times some length scale divided by nu, where nu is the viscosity, kinematic viscosity. And Richards number will give us the ratio of these two, Grashof number to Reynolds number square. And if this number is greater than 1, then the Grashof will be dominant, or if it is less than 1, then it will be Reynolds number will be dominant and it will enter forced convection. And this close to 1, we would call that a mixed convection problem. So this classification is based on who drives the fluid. And then there are other classifications also. And why is this important? Is because when we are solving a problem, we would always encounter like solving a problem as a mixed convection is much more difficult than solving it as a pure force or a pure natural convection. So hence we have to first evaluate this number and decide which of the terms in our governing equations are important for the particular problem that we are solving. And that is one thing that this particular course helps you to understand when you have, like as I said, this course is only gives you the alphabets of this convective heat transfer. So first you have to understand the existing solutions for some of the basic cases that are there. And then you try to make up your case by kind of adding these cases together. That is also something which we will discuss later in like week 3 or week 4, where you will build upon whatever simple solutions that we already built and use them. It's not a simple linear superposition, but then the idea is how to extend from the basic concepts that we discuss in this course to some of the problems that happen in real time. We will take up some example problems on that also. The professor will also be discussing some tutorial questions where you can extend the ideas that are discussed in the course to some real world problems. The other types of classification are again based on what is relevant. Say we have, let's say we have a solid plate or something, and some flow is happening around this. Like I'm not drawing how the flow is going to be, but let's say some flow is happening around this particular solid. So the fluid over very far from the plate will not even notice the presence of the plate. So there is a certain region in which the effect of the plate is dominant, and beyond which that effect kind of diminishes. So that particular region is what we call a boundary layer region. So based on how far the effect is felt, again we have two different kinds of flows: external versus internal flows. The idea here is when external flow is one where you have an unconfined or an infinite boundary on one side. So essentially this flows as if there are no other things in that are restricting it. While the internal flow is one where you have a confined one, like let's say the flow that is happening inside a pipe, where any fluid particle here will know the presence of both the walls. What do I mean by know the presence of both the walls is, if the walls were not there, you would have a certain kind of velocity, and because of the presence of the walls, the velocity would have been affected. How is that affecting is something again we will discuss once we move on to internal flows. But initially there will be two kinds of regions in this. So there will be a certain region up to which the fluid here will not notice the effect of both the walls. So it is as if, even though it is a flow inside a pipe or a channel or something, the flow here that is going to happen will behave as if it doesn't know the presence of the other plate. So it sees only one plate, but beyond a particular point, it kind of sees both the plates. So this particular classification of external versus internal or forced, natural, mixed, these are not like a universal thing for the entire problem. So if you are solving some complex problem, there could be certain regions where, for example, even in the previous case, as we use the Richardson number, this is not a universal constant for the entire domain that you are trying to solve the problem for. There could be certain regions in the domain where Grashof number is dominant. There could be other regions where Reynolds number is dominant. So similarly here also there could be certain regions where using the concepts from external flows can help you, and there could be other regions where using the concepts from internal flows would be helpful, and there could be regions where these are kind of mixed. So these are also the things that we'll be discussing in the course as we go through. And knowing, and we also need to understand what happens if you mistake the flow. For example, if there is an internal flow and you take it as an external one, or the other way around, how much error would that give you in your predictions is also something that we would be looking. So that helps you to understand why this distinction is important, why we are trying to classify all these kind of stuff. And apart from this, we also have the other types of classifications, as in incompressible, compressible for the fluid mechanics. But since you're already from fluid mechanics, I'm not going into that. But just to write it down. So here in this course, we'll only be discussing incompressible flows. So what do I mean by incompressible flows? You can unmute yourself or you can type in the chat box, whichever. Just want it to be interactive. So if you have any questions, we can discuss them also. We have one more classification before incompressible flows is laminar versus turbulent. This is also something that we will cover. Initially, most of the lectures will be on laminar flow, and towards the end of the session, like week 11 or so, we will be discussing turbulent flows. But up until then, we'll only be discussing laminar flows. What is the differentiation, like the laminar versus turbulent flows, and that would require an extensive class on itself. So I would postpone it till week 11 or week 10. When we discuss turbulent flow, then this distinction will be apparent. Otherwise, now it will be like fairly to understand. In simple words, a laminar, you will have a layer-like structure to the flow, where if you kind of put some probe at somewhere inside the flow and try to measure the velocity or something over there, that would be fairly, like, you would not find any random spurts of noise if your measurement system is good enough. But in a turbulent one, we would be seeing some kind of oscillations around, say if I were measuring at some particular point in a laminar flow, there could be unsteadiness, but there would not be complete randomness at that particular point. But if I were seeing turbulent, I would see some kind of burst around that. How do we quantify this burst, and how do we kind of do some kind of averaging to remove this thing, and how do we treat unsteady, and all of that we will discuss in week 11. But for now, the idea is laminar one is like a simple flow where you do not have any scales. Again, scale is a word that I have not introduced before. But the idea in laminar flow is you have a layer-like flow, so you can you have the streamline, streak line concept that we discussed before. Once we move on to turbulent, then we'll be having these small disturbances that will be coming that have to be accounted for, and they kind of increase the heat transfer in certain scenarios, and they also decrease the heat transfer in certain scenarios, depending on where they occur. And so we need to have a basic understanding of when they increase the heat transfer, and if you have a particular application where you need to increase the heat transfer, how to introduce these turbulence into the flow so that your heat transfer will be increased. And the next aspect that comes is how do we model turbulence. That is also something that we will discuss in week 11. So these are the general classifications. Yeah. So coming back, so what do we mean by incompressible flows? So density is constant. So if I have, let's say, uh, a problem where you have natural convection, or let's something like the one that I told just before. So you're sitting in a room. Let's say sunlight is falling in one of the walls. So this wall will have a temperature which is higher than the room temperature. So this is my room. So if I want to study the fluid motion inside this room, so density will definitely vary because I'll have some natural circulation that is happening. The hotter air, like the air which gets hotter, will raise upwards, and the cooler air that is coming because of your air conditioning system will move down because it has a lower density than the warmer air. Sorry, it has a higher density than the warmer air. It flows down, and the hotter air moves upwards. So clearly, density is not constant here. So is this like, can I use incompressible flow assumption in this particular case? Or maybe I should say that this we can actually use incompressible case. So like we can be a little more formal as to what the definition of incompressible flow means, because we will be using this throughout this particular course. So there will not be any case where you do not have this assumption being taken. So in a real world problem where you might have to come up with your own model equations, you need to check certain things like check whether this assumption is valid or not. So how do you check whether this particular assumption is valid for the scenario that you are likely working with? What is this density for a fluid a function of in terms of the fluid properties? I mean, in terms of the thermodynamic quantities, the density is a function of temperature. We know, like I just told. What other quantities is it a function of? Say, let's take an ideal gas for example. For an ideal gas, we have PV equals to nRT, where N is basically the mass divided by molecular weight. So from this, I can get density as for a given gas or a mixture of gases. So we have M and R. R is the universal gas constant. M is the molecular weight of that particular gas. So these are constant. So the density is a function of both pressure as well as temperature. So when we say density is constant for incompressible flows, what we essentially mean is the variation of density with respect to the changes in pressure are negligible. So what we mean by this term is, if I were to write d rho as something like this, then what we essentially mean is this particular term, the change in density with respect to the pressure is negligible. When this is approximately zero, then we would call it an incompressible flow. And under those scenarios, this essentially happens when you have flow that is happening at very low Mach numbers. So this d rho by del p is going to depend on the speed of sound inside the medium. So indirectly, this would eventually evaluate to the Mach, like it will be written in terms of Mach number. So if you have Mach number less than Mach number is essentially the velocity of that particular fluid divided by the speed of sound in that particular fluid. If this is less than say around zero point 0.3 or so, the variation becomes around less than 10% of the total change in density, and then we can neglect this particular variation. When this particular one happens, then my continuity equation will essentially reduce to del dot u equal to 0. And this is the equation that we'll be using throughout the course. So whenever I say continuity from here onwards, I essentially mean del dot u equal to 0. So there are no density variations that I am accounting for. There could still be density variations because of temperature, but that would not come in my continuity equation. If you are interested, you can also go through the derivation of continuity equation and how this particular term evaluates in case of different temperatures. And so there is some book by book of compressible flows. You can refer that book where detailed discussion is given. But the idea that I want to bring here is all you need to be checking is whether you have a Mach number for in your particular scenario, in your particular problem of interest, is the Mach number less than 0.3 or so. If it is, then you can use this equation del dot u equal to 0. If you have higher Mach numbers, then you have to move on to compressible flows. I think that is clear. Okay, so that is the basic introduction that is discussed in these videos, and then the recorded session will move on to governing equations, which are essentially for a fluid flow. We have, as I said, the continuity equation, and then we have the Navier-Stokes equation, assuming Newtonian fluid with constant properties. So the equation will be rho times du dt, where d dt is the material derivative given by the partial derivative with respect to term. This is the unsteady term, and then we would be having, this is my advection term. So the net force on this will be given by negative of pressure gradient. So this term essentially says that whichever direction the pressure gradient is, the flow will happen in the reverse direction. So if fluid flows from high pressure to low pressure, so it should happen in the reverse direction of pressure gradient. That is the negative grad P. And then we have the body forces, which is essentially the gravitational force or any other body forces you might have. So rho times B bar. I'll just write rho G bar for now. And then we have the terms coming from viscous dissipation. So that will be constant properties. So I'll just write it as mu times del square bar. So depending on the coordinate system you use, you can expand this vector or like the operators, and then you will get the terms accordingly. Hope you're already familiar with how these equations came and what their assumptions are. That is the kind of a prerequisite for this particular course of fluid mechanics. So what we will be doing in this particular course is, since we already know that we cannot solve this equation directly, there are different ways we can use computational fluid dynamics, which we will discuss in week 10 of this particular course. And there are some other simple problems where these equations, some of the terms can be eliminated using different techniques. So the one that we'll be discussing in next week is something called a scaling analysis, where based on some experimental results, we get an order of estimate, like order of magnitude of each of the terms that are in this governing equation. And then we will find out which of the terms, like when we compare each of these terms, some terms can actually be neglected. And that will reduce these equations to some simplified form that can actually be solved. And that is what we will discuss in the next week. We will derive the equations and we will kind of solve them under some simplified assumptions. So for this week, only these equations are given. So for those of you who are just write it in only for the x momentum, just to get familiar with it. So if I want to, this is a vector equation. So if I have to write only for the x momentum, so the equation will be del u del t plus u dot del will be u times del u del x. Again, this is a vector, so v times, since the equation is being written in terms of x, so we have del u del y plus w times del u del z. We have the pressure, this entire thing is multiplied by density, is given by pressure gradient minus del p del x plus the body force term rho times gx. Gx is the vector component along the x direction for the gravity, and then we have the viscosity term. the Laplacian operator acting on the x component of velocity, which is del square u del x square, del square u del y square, del square u del z square. Similarly, you can write for y and z momentum also. So these are for the, again, this is for mass continuity, this is for momentum, and then we have one more equation that may not have been discussed in your fluid mechanics course, is for energy transport. So like an energy conservation equation, and that is also something that we will discuss in the next week. In the next week recorded lectures, you can find the derivation for like momentum and continuity would already been discussed in fluid mechanics, so that is a prerequisite. And how do we extend from there to energy conservation is something that is discussed in week 2. Now this is kind of some simple problems where just to kind of refresh your concepts. So we start from the Navier-Stokes equation. And let's say for a hydrostatic case, which of the terms would be zero or can be neglected? This, and we also have continuity. A hydrostatic problem is like, let's say you have tank on your rooftop and then there is water inside the tank. Let's say the tank is completely full, like it is completely full with liquid. And you want to see the velocity vector field inside this tank. So what would happen to my governing equation? So this is like a very simple scenario where the entire water inside the tank is stationary. So our U is 0. So all the terms will essentially go to 0 and we'll be left with grad P equals to rho times G bar. And again, if we consider this as my Z direction, X, and then we have Y, then P is only a function of Z. So we have dp dz equals to rho times minus G. If I integrate this, then I'll be getting P z equals to 0 minus P z equals to, let's say this is the height of the tank. This is an equation that you are already familiar with. So just reverse the sign here so that you would get this equation. So this is something that we already know. So just to show that this comes as a subset of what we already like from the Navier-Stokes equations. And then let's take Bernoulli's equation. How do I, so when is Bernoulli's equation valid? Again, we start with the original equation. Let's for now not consider the gravity term, but you already know what happens with the gravity term. So this is my equation. Under Bernoulli's case, how would this reduce to? What are the assumptions in Bernoulli's equation? So Bernoulli's equation essentially says, so if I have a fluid flow that is happening in under steady state without any viscous forces, irrotational, and under all those cases, like we have, if we expand this term, so this will become del u del t. Let's say we have only flow along the x direction. Just to kind of simplify this, that will be u del x is given by minus del p del x. Because the fluid is like viscous effects are neglected, we will ignore this term. If the fluid is irrotational, also this term goes to 0. So this would be my equation, steady flow. So this equation goes to 0. So I have dp dx plus rho u du dx equals to 0. So this essentially comes down to p plus half rho E square equals to constant. Of course, gravity term is neglected in that. So this is the Bernoulli equation that you're already familiar with. So what are we trying to do here is just to show that some things that you're already familiar with are also coming by some simplification of the Navier-Stokes equations. So in order to get at this solution, we already used some of the facts that we already know. Like the flow is irrotational, so I can reduce this particular term. So in the previous case, I know that fluid flow is not happening inside this one, that the fluid is stationary. So if I were to measure velocity at any point, it will be zero. So using that fact, I was able to reduce the Navier-Stokes equation to this equation, and I was able to determine the pressure. So similar strategy, similar technique will be used for in the next week when we derive something called like first we derive energy equation and then we move on to boundary layer equations, where people have done experiments and they measured certain quantities, basically the terms inside this equation, and then from there we will eliminate certain terms, which gives us simplified equations, which we will solve to determine different quantities of interest like I said in this particular case, how far is the solid affecting the fluid flow boundary, and what is the net reduction in the momentum of the fluid because of the presence of this solid due to viscous forces. What is the, for example, if this particular plate is heated, then what is the net amount of heat that is transferred when a flow is happening here? And if I want to increase the heat transfer rate, what should I be doing at the solid surface? What should I be doing at the fluid surface? Sorry, what should I be doing at the fluid boundaries? These are all the questions that we can answer once we get the simplified equations. So that is the exercise that will be carried out in the next week. Yeah, so these are the things that are discussed in this week. So do you have any specific questions that you want me to discuss? Otherwise, we'll quickly summarize this. Like this week is mainly an introduction one. Or you want to discuss anything in particular that you want me to include in the upcoming sessions, I can do that as well. Assignment problems. Do you have any specific questions in the assignment problem that you have query for, or is in general? Any specific question? Like there are some 8 problems or so. This week is more like the basics. So for this particular week, your problems will essentially revolve around knowing a couple of things. The first one, as I said, like most of them are already discussed. I was saying this one. A few more equations that you would be requiring are the ones. Maybe I can summarize this and you can find what is required for these sessions. Knowing this would help, like how to determine heat transfer coefficient and what are all the things that affects the heat transfer coefficients. And essentially, when you have a solid and a fluid interface, then how do we determine the heat transfer using the Fourier law of conduction and the heat transfer coefficient? So this is another thing. And apart from this, there are a couple of other things also. Yeah, I should also discuss one more concept. Do you have any specific question that you have problem with? There is one more concept that is being discussed in assignment problems is the concept of Nusselt number. That is again a non-dimensional number that is used to assess whether your particular configuration is being helpful than conduction or not. So essentially it transfers, yeah, okay, sure. So Nusselt number is essentially the ratio of heat transfer due to convection divided by conduction. So it tells us how many times or how far, if this particular number is greater than 1, it tells us how efficient your heat transfer is happening because of convection. So in general, if you have a question about any assignment problems, I usually uh, design this particular live session based on assignment problems itself. I'll be taking more problems than the assignment questions also. in general, most of the questions you will be able to answer once you go through the session. If you have any specific query as to like if some part of the question is not clear, you can bring that up also. The idea of these sessions is to help you solve the assignment problems. Okay, then are there any other questions? And regarding exam, those of you who are appearing, who are going to appear for the exam, like you're going to credit this particular course or something, then you might have to, the type of questions that you would expect in exam would be at the similar level as your assignment problems. Like they will not be the ones that we'll be discussing in the live sessions, but they'll be close to the assignment problems that you are, the weekly assignments that you are solving on the course website. Those are the kind of problems that you can expect in your final exam. Almost like around 60 to 70% will be the questions directly from those assignments, and there will be some other changes in few other questions. But more or less, the level of difficulty and the type of questions, essentially, you will get MCQ. Just like the pattern would be very similar to what you are doing in your weekly assignments. That is as far as the exams are concerned. Any other questions? Exam is going to be online, but you have to go to the center for the exam. The details of that will be circulated to you in the announcements portal. If you, once that is circulated, if you do have any queries, you can raise it on the discussion forum, and the NPTEL admin team will actually respond to that. But it is going to be an MCQ one online exam, but you have to go to the center. The details of which will be again given to you later in the announcement portal. Okay, guess there are no further questions. Okay. If there are no further questions, like what we discussed, to summarize, what we discussed in today's course is solve more problems like as assignment problems. Yeah, sure. Yes. So from next week onwards, like you will be solving numerical problems even in the assignments. So we'll also take up example problems from the reference textbooks, and then we will solve them. This week is more like a theoretical one, so I do not have many numerical problems, but I can give some problems if you would like. Okay, you're not from heat transfer, so I can give you some problems to work on. Yeah, we can take up some simple problems. Because you are not familiar with heat transfer in conduction and so on, you can take up a conduction problem. Let's take a simple problem first. Then let's say I have this problem is very similar to the one that you will be solving in the assignments also. Like the one I said, you have a heat exchanger. Heat exchanger is one where you have, let's say there are two pipes, and then there is a pipe inside that one. So some fluid is flowing on the inside pipe and some fluid is flowing on the outside pipe. So we know what is the, so just to differentiate this inside and outside one. You can think of the outer one like a jacket inside which another fluid flows, and there is one fluid flowing here. The flow rate on the outer one is given by, let's say, m dot out, and this is m dot in. And then we will also be given the temperatures. Let's say this is T1, T2, T3, and T4. So that basic, whenever you like even in assignments, the problems that you will be given are like this, where you have to apply. First is the mass, like we have only have three conservation equations: the mass conservation equation, momentum, and energy. These are the only three equations that you will be using. And in this particular problem, whenever heat exchangers, etc. come, momentum equation is not even used. We'll be only requiring mass and energy equations. And in this particular case, the pipe is of uniform cross section. Like mass conservation essentially says the m dot remains constant as you go from the pipe. So which is also not used. So only equation that is left is the energy balance equation. So how do we define the net heat transfer rate across this surface? So if I take the fluid inside this pipe, the net heat transfer rate is given by m dot in times Cp. If fluid is flowing in this direction, out minus in, which is T2 minus T1. That will be the net heat transfer that is happening for this particular fluid, and this should be equal to the net heat transfer that is happening because of the outer fluid. So you will have only one equation. So at most you will be asked for one unknown. So remaining all quantities should be given to you. Or like in the particular assignment problem, you will be given the heat transfer, heat flux value. This would be one way in which the form problem can be given. Or there could be another scenario, like I was saying, you have a pipe in which the heat flux value, there is some heat flux that is happening from the pipe walls. This value will be given to you. So as I said, this entire course will only be having two variants of the problem. You will be given heat flux and you'll be asked to find the temperature, or the other way around. You'll be given temperature and you'll be asked to find the heat flux. It would be one of these two cases. So if the heat flux value is given to you, how do you estimate the temperature from there? Is again you apply an energy balance equation where QW prime is watt per meter square per unit surface area. So you just have to integrate it across the total area. This will give you the net heat transfer that is given by the flow rate times delta T, the temperature difference that is going to happen. M dot is the mass flow rate, Cp is the specific heat of that particular material. Or it could be the other way around. You will be given the temperature difference and you'll be asked to find the heat flux, whichever is the case. So this is how usually it goes around. And then there are other variants of the problem where these are for internal flows. And then you can also have external flows where you have, let's say, this is some plate or surface that is heated at a temperature greater than the ambient. Or let's say this is some solid object where the temperature profile is given to you. And you are required to estimate the Q double prime. So how do we solve this kind of problems? Is again, as I said, you have to use this, the continuity at the interface, which essentially tells you that the solid temperature at the interface should be equal to the fluid temperature at the interface. And the second equation will be minus if this is my y direction, del t del y, and let's say this is my origin at y equal to 0 should be equal to Ks is the thermal conductivity of the solid, Kf is the thermal conductivity of the fluid times del t del y at y equal to 0, where this temperature will be the fluid one, this will be the solid one. So you need to know the temperature profile in the solid, you need to know the temperature profile in the fluid, then you can equate this and then you can estimate the interface temperature. If only one of the temperature is given, then you can calculate the, like one of the temperature field is given, then you can use the properties of that particular material and then use the Fourier law of conduction, which gives you the heat flux. So these are the only kind of problems that we can solve for this particular week. Next week onwards, there will be other questions also. So most of the times we will not be knowing what this quantity is going to be. We will be only interested in the fluid properties. And then also, as I said, most of the times we'll only be given the T infinity, which is the ambient temperature very far from the solid of interest. Then how do we relate these two quantities? In that particular case, as I said, QW is going to be heat transfer coefficient times the surface temperature minus T infinite, where H is an unknown that we need to estimate. So the usual way to go about this, again, the same thing that we will carry out throughout the course, is we use non-dimensional numbers, just like Reynolds number, Grashof number, etc. For heat transfer, we have Nusselt number, which is given by H is the heat transfer coefficient times the characteristic length divided by the thermal conductivity of the fluid. Again, just to keep a note, whenever you are giving solid fluid, etc., just understand this is a property of the flow that is happening. So this is happening inside the fluid. Convection is happening inside the fluid. So all these have to be with respect to the fluid. So since H is a function of different quantities, Nusselt number will also be a function of fluid, flow properties, geometry, etc. So for every particular geometry, we'll list out, like as we go through the course, we will derive different correlations, different relations for this Nusselt number. And this Nusselt number is going to depend on, as I said, the fluid flow geometry. So all of these will be clubbed together in further non-dimensional numbers like Reynolds number, the some dimension, characteristic dimension, like the aspect ratio of the, which we will see later, or it could depend on Grashof number, it could depend on the Richardson number, like I told before. There are different numbers. So we will first identify, okay, for this particular geometry, what are the non-dimensional, like we will non-dimensionalize the governing equations, and then we will come up with these numbers, and then we will estimate this Nusselt number, and then we will find the functional relation between this Nusselt number and these non-dimensional numbers, and that functional relation will keep changing depending on the problem that we'll be encountering in this particular series of lectures. So all you have to be doing is you pick out the particular problem of your case, see which of these existing functions closely resemble to your particular problem of interest, and then estimate Nusselt number, and then use this to estimate H value. And then you can either find, like if the heat flux is given, you can find the surface temperature, or the other way around. If the surface temperature is given, you can find the heat flux. This is the general flow of how you solve all the SML problems that will be coming in upcoming lectures. And then, yeah, I think I missed out on another important point. So when we discuss the governing equations, we should also be discussing about the various kinds of boundary conditions. These are very similar to what you would be doing in your partial differential equations. We have the Dirichlet condition, which essentially means I have to specify my velocity on the boundaries, or I would be having Neumann condition, which essentially gives the on that particular boundary, we will be giving the gradient of velocity equal to 0. Or some kind of mixed condition, depending on problem to problem, this will change. These are only with respect to velocity. As you can see, the main problem with these equations uh, is because here we have an unknown u as our unknown, and pressure is also an unknown. So we have two unknowns, and these are essentially two. Essentially, this is a vector equation which will again come up to as three different equations. So I have four different equations and four unknowns, which is the u vector, which has three unknowns, three components, and then my pressure as a scalar. So solving this system of equations is complex essentially because pressure is not appearing in my continuity equation. So how do we solve this is something that is important and which will be discussed in detail in week 11. But for now, most of the cases when we solve in the upcoming weeks, we will assume that the pressure gradient is negligible. So this particular term is completely gone. So then we'll be like we'll have some simplified equations that we can solve. Yeah. So in general, these are the kind of assignment problems you can expect. Yeah, maybe exact numerical problems I'll bring up next week. Yeah, I'll take that as a feedback. I'll have some numerical problems from next week. So, and maybe I can give you some time to solve them during the live session itself. So you'll have like every problem some 5 to 10 minutes I can give where you can solve those also. So that way it will be much better, I guess. Any other questions? Yeah, and I also have a feedback form, so you can fill in essentially to see whether any type of feedback that you want to give, you can give on the feedback form, and then to assess whether the pace is okay. If the pace, like if I'm being too fast or too slow or anything, you can also tell that. You'll also be circulating, the NPTEL team will also be circulating you a feedback form regarding the recorded sessions. That also please do fill in if you have anything to, like any doubts or anything regarding the recorded sessions also. Yeah, so these are the pretty much ones that I have for this particular week. Okay. To quickly summarize, we started out with uh, the general introduction of the course and what to expect in this course. I can quickly outline the course layout also. So we started with what are the different kinds of heat transfer: conduction, convection, radiation. And from there, we narrowed down to convection, which is of our interest. We concluded that this convection is going, the problems that we will encounter here will be something of this kind, where our objective is to estimate the heat transfer coefficient, like one of these quantities. And it is something that is going to depend on fluid properties, flow properties, geometry configuration of the particular problem that you are interested in. We have seen a couple of applications of convective heat transfer, like in heat exchangers and HVAC applications, like heating, ventilation, air conditioning systems. And there are several other applications that are discussed in detail in the lecture videos, which I'm not kind of repeating again. And then we understood different classifications of flow depending on what is the driving force, whether it is happening across the boundaries or it is happening because of some body forces, or it could be because of both of these. And how do we identify these regions based on some kind of non-dimensional numbers? And why this is important is because it helps you to pick the correct solver for the problem of your interest. We also classified as external versus internal flows depending on how far the influence of the solid is going to happen in your particular domain of interest. We also discussed different laminar versus turbulent, which we will discuss in detail in week 10 or 11. And then we also discussed about incompressible flows, which essentially means the changes in density with respect to pressure are negligible. Subsequently, we discussed on the governing equations, essentially the Navier-Stokes equations, which is an essential prerequisite for this particular course, the derivation of which will not be covered in this particular course. In addition to the mass and momentum conservation, we will also have energy conservation equation, which is essential for this particular course and will be discussed in next week. These are some simplified cases where Navier-Stokes can be reduced to. And the types of problem that you would expect is in this particular course, we usually have to do with either finding temperature or finding the heat flux. So you need to estimate the heat transfer coefficient, which is given in the non-dimensional form with the Nusselt number, which is given by this equation. And this Nusselt number is going to be a function of the particular fluid of interest, the flow geometry, etc. So what we do in the upcoming sessions is we first write the governing equations, like derive the equations for our flow, simplify them by making certain assumptions, and then come up with some non-dimensional numbers that can characterize the geometry of the flow of consideration. And then we will find functional relations between the Nusselt number and these non-dimensional numbers that we will find. So this functional relation will keep on changing. So we have to pick the correct relation for the problem of your interest, determine the H value, and then we can find one of the unknowns from this equation. So the general layout of the course is this week we said like intro and basic foundations. Next week we will start with the energy equation derivation, energy conservation equation, again in terms of differential form. And then we start with the boundary layer equations. This is like initially we will start with external flows. As I said, the questions of interest here are, I have a solid surface and I have a fluid flow that is happening around the solid surface. How is the fluid flow affected because of the presence of the solid? How much momentum is getting reduced? How much heat is being transferred from the solid to the fluid? These are all the different types of questions that we will answer in boundary layer equations. Initially, we will start with the assumption that there is no pressure field, there is no pressure gradient, and then we will move on to scenario where there exists a pressure gradient. And then this will be with respect to forced convection, external flows. And then in upcoming weeks, we will also discuss on internal flow. So this is external flow because it is confined only in the one direction, like it's like a semi-confined one. And then we move on to confined flows where you have two walls or something to bound the flow on either side, like from either side, so that the effect of the fluid feels the effect of walls on every side of this flow. So this again the same concept. We'll start with the governing equations and then we will discuss. We'll find out what the non-dimensional parameters are going to be, and then relate them with the Nusselt number, get the functional correlation, and then we will solve problems on that again. So that is with respect to both of these are with respect to forced convection, and then we'll again follow the same strategy for natural convection flows. I think this is up to week 5, and this will be week 7, 8 or something. I think not sure about the week numbers, but then we will move on to natural convection. Like I said, in forced convection problems, the main driver is the forces that are happening at the boundary. In natural convection, we'll have a buoyancy force, that is a body force, which will be acting throughout the volume of our interest. Again, here we will do the same cases, an external and internal. And solving internal flows is like kind of quite challenging. So then we will move on to, from this we'll move on to CFD, computational fluid dynamics. We will set up the governing equation. We'll actually solve some simple problems. We'll have this is not like a full-fledged CFD course. So the idea here is to give you a brief overview of how to translate the governing equations, like how to discretize them and convert them into a framework, so that you will convert them into a system of equations of the form Ax equal to B, and use where x is the unknowns that you're trying to solve for, and we'll find the values of x. So this is just to give you an idea of how this flows and what are the some of the basic challenges that you'll encounter when you do a CFD simulation, like when you want to convert your problem from analytical to a CFD one, to just give you an overview of that. And once we are done with that, the major class of these flows are open. All these up until then would be laminar flows. By around week 10 or so, we would be entering turbulent flows. We define turbulence, we define different in this, and then we will discuss about how to identify turbulence, like what are the quantities that are used to differentiate turbulent versus lambda, and then we will discuss Reynolds average Navier-Stokes equations. So the governing equations itself will be difficult. Again, how do we model turbulence? We will discuss some of the experiment, like some of the experiments that are done, and then we will see something called universal law of fall, which helps us to model turbulence in some ways. We'll also see what are the limitations of the models and how to extend them, like what are the things that you need to consider when you are using them in a real case scenario. We will not discuss all the detailed models. Again, to those of you who like just to set the expectations clear from the course, we'll not be discussing in detail about different trans models, like how to use which model to use when and stuff like that. The idea here is to essentially derive the RANS equations so you understand the general framework, and then from there we will present universal law of fall, which tells you how to if a model is existing model is there, how do you evaluate the model. That's the only thing that we'll be discussing in this particular course. It's like you'll understand what are the different terms, like what is y plus, and these are how do you know whether your particular turbulence model is resolving the scales correctly or not. Those are the only questions we'll be answering, but we will not be comparing or giving you anything discussing on which turbulence model to use for your particular application or not. Those are the things that are not discussed or in this particular course. Once we are done with turbulence force, then eventually the last week of the session, the last week of this course will be on phase change, which is for boiling condensation, essentially evaporation, condensation, and boiling. We'll discuss that, and with that we will end this particular course. And yeah, and to kind of summarize on the assignment problems. Again, as I said, the aim of these live session is to help you solve assignment problems. So please go through the lecture videos before joining the session. And if you do have any queries, you can raise them during here so we can discuss them. And yeah, since assignments are graded, we will not be discussing the exact assignment problems. So I'll be taking problems similar to the assignment questions and we'll be discussing them so that they can help you to solve your assignment problems. And once the assignment solutions are out, then if you do have any questions, we can discuss them during this session also. And as far as the exams are concerned, they're going to be online, multiple choice questions, and the difficulty level, you can expect them to be similar to the assignment questions that you are solving now. Yeah, so this is pretty much the summary of this week. If you do have any feedback, please fill in the feedback form. Yeah, I'll wait for like 5 to 10 minutes. If you do not have any questions, feel free to leave the session. Yeah, I've noted that from next week we'll have numerical problems also, wherein I can give you like 5 to 10 minutes to solve each question. We'll pick up like 10 problems or so. So that should give you ample time to relate the concepts that you have learned in the recorded sessions. Yeah, do you have any questions? Yeah, if you do not have any questions, feel free to leave the session. I can wait for like a few more minutes and then we'll end the session. Yeah, so no questions. No any questions. So saying you do not have any questions. So are you asking that we have discussed any questions or is it like you have no questions? Yeah, thank you for filling the feedback. Okay, and see you on next week. Yeah, if you do not have any questions, then I think we can end the session for this week. I'll wait for a few more minutes. Yeah, sure, you can leave. Just wait for a few more minutes. So if anyone joins who has any questions they need to ask, so the session has to be open. So if you do not have any questions, feel free to leave. Yeah, you can leave. Yeah, sure. We'll take up numerical problems because this week has mostly on the introduction part, so I do not have numerical problems. We'll take up numerical problems from next week. Yeah, I guess that is it for this week. Thank you for joining, and then we'll meet next week. As I said, we'll be starting discussion on derivation of energy equation, and then boundary layer equation. We'll discuss the assumptions, the experimental data from which those assumptions were derived, and then we will conclude with the derivation of boundary layer equations with and without heat transfer. The solution of which we will discuss in the upcoming week. Thank you for joining. Yeah, any other questions? I guess there are no further questions. Yeah, we will solve more numerical problems. Thank you.